All right, one of the things I wanted to show you was this program called Graphing Calculator, which is available on these computers, and it's also available in the STEM Center. And if you're interested in purchasing it, it might be a worthwhile buy. But there are other things that exist online. I'm too lazy to find them and give them to you, so you have to find it yourselves. But this is fairly easy in the sense that you just type in any relation between x and y that you want. Oops, it should be x to the fifth. And then you get the graph instantly. What's cool about this is that you could type in another relationship where it's not necessarily a function of y, and this is where your handheld graphing calculator doesn't get to do this very well. And then you get that other function that you wouldn't normally get in your regular graphing calculator. And even more interesting is that you can grab your cursor and drag it along a curve, and then if you get to an intersection or an intercept or anything like that, it'll snap so that you can see that these two curves intersect at negative 0.8 and negative 0.4. And then you can continue on. You see the intersected 0, 0, and then intersect this other place. So this is one of your homework assignments. Another thing this is good for is that you can actually graph parametric curves. So this graphs this parametric curves, but it gives this limit of 0 to 1. So if I want to go from 0 to 2 pi, I just press enter, and then I get that. And I can use these windows. You know how you, in your windows, for your graphing calculator, you have to go to Windows and set the X and Y window, and then set the T window parameter. Here you can do that really quickly by just zooming in, zooming out, or moving this around to get a view of what you need to get a view of. And where in the graphing calculator, if you're in a parametric form phase, then you can't do a regular graph. Here you can do both a Cartesian graph and a parametric graph, and then you can see it all at once quickly. So there are nice online programs that do this as well, but this one I find to be really easy, and it was available to me for free, so you just would have to pay for it if you want it. So I was thinking about using this every once in a while if we need to visualize something. By the way, this is goes beyond just the two-dimension stuff. So later on we'll be talking about surfaces, and so this would be another good quick tool to be able to graph surfaces. And then you can view it from many different ways. All right. So today we will continue on with our discussion of tangent lines, and then go over and do some more calculus with finding areas and arc lengths. So here is our formula for finding the slope, and here are some examples that we could do. I think number 5 might be one of those questions that's similar to a homework question or something. Or we can do number 6. What number do you guys want to do? Let's do number 6. So we want to find the equation of the line passing through the point when theta is equal to pi over 6. And here they call it theta instead of t, but that's just another name for the same parameter. So let's say we need the point, and then we need a slope. And once we have those two things, then we can just plug it into our point slope formula. So to get our point, we need theta to be pi over 6. So x is going to be equal to sine cubed. Is that cubed? Sine cubed pi over 6. So what's sine pi over 6?
That's 1/2.
1/2 cubed. And so this is 1/8. And the y is cosine cubed pi over 6. And cosine is root 2 over 2. Root 3 over 2 cubed. So I'll just say 3 to the 3/2 over 8. So that's your point. We need the slope, so we need to take the derivative of each of them. Let's take the derivative of y first. Let me put this down. 1/8, comma 3 to the 3/2 divided by 8. So that's your point. Now let's find our derivatives. To get the derivative of y, it's 3 cosine theta squared times the derivative of cosine is negative sine theta. And then we want to put pi over 6 there. So put pi over 6. So cosine pi over 6, you guys said was root 3 over 2. And sine, you said was 1/2. And then x prime of theta is 3 sine theta squared times derivative of sine is cosine theta. Evaluate that at pi over 6. So 3 times sine theta, you said sine was 1/2, and cosine was root 3 over 2. So you need to put them in the ratio as a fraction, one over the other. Y prime over x prime is equal to 3 square root of 3 over 2 squared times negative 1/2 divided by 3 1/2 squared times root 3 over 2. Kind of kept it like this because I could see things cancel a little bit easier. So I have a root 3 over 2 and 1/2, so the 2's also get to cancel in the bottom. So I just have a negative root 3, is that correct? Wow. After you do all the canceling. Is that right? Okay, just a couple of nods. That's all it takes. So we got the point, we got the slope. We'll put it in our point slope form. Y minus y1 is equal to the slope times x minus x1. And there's your equation. Okay. It's always good to check to make sure we did this correctly by looking at a picture of it. Let's see if we can look at a picture of it. First, we have to make sure that this point is on the graph. Well, first we should probably draw the graph. Which one was first? The sine was first. Sine cubed, oops, sine t cubed. Now I know it says theta, but this particular program has certain variables. They use certain variables for certain things. In this case, the parametric equations, they use t. Cosine. Maybe I should put parentheses around here just in case. It's a small graph. There it goes. So it looks like a little asteroid thing. Now, at pi over 6, was it? Is where our point should be. So pi over 6 is, when t is equal to pi over 6, we're at that point. You see that point? Now let's try to draw the line. So our line is y minus 3 to the 3/2 power divided by 8 is equal to negative square root of 3 times x minus 1/8. So that looks fairly tangent, right? So that must mean we did it correctly. That's good. Where's this going to go? There it goes. It'll be in there in your notes somewhere. What if we just shrink it? Can't go too low. All right, any questions about doing one of those problems? All right, let's move to our next calculus idea, and that is to look at areas. So in this particular text, they took our regular area, finding the area under the curve. When they say area under the curve, they mean the curve in the x-axis. And then they extended that idea to apply to a parametric curve, and this is what they come up with. So basically what happens is that you got f of x dx, and what we're hoping, you know how when we have parametric curves, it allows us to draw curves that might not pass the vertical line test of a regular function. And so what we're going to assume is that on an xy plane, we're only going to look at a piece of the curve that is going to pass a vertical line test. So in this case, you might have a curve, a parametric curve that goes from, let's say, A to B. But instead, what we're going to do is that we're going to focus, we're going to cut up this curve and only take a little bit of the curve that would pass the vertical line test. So instead of focusing on that whole curve, maybe we'll just take this piece of the curve over here. Okay. Whoops. See if I could do some magic here. Oh, man. So then I'd be looking at a small piece of the curve instead of the whole thing. So then now it makes sense to find the area under the curve. Right? So that's what we're going to do. And when they say that x of t is 1 to 1, that's basically saying that if you go along the x, it's not going to come back on itself. And so I mean, you guys should know what 1 to 1 means. It was done in pre-calculus, but because it wasn't really stressed in other classes, you might have forgotten. But that's what that whole idea of 1 to 1 means, is that it doesn't wrap around itself in that sense. So in any case, because now we can try to consider this as y as a function of x, that's kind of like what's going to happen here. Your f of x will be like your y, and then your d of x is going to be like your x prime of t. And then so you tack on that extra differential and make sure you can integrate it. So that's the slight change in the way we're going to approach this, but in general, this is coming directly from our formulas. Notice also that this is a and b, but now your limits here are limits of t, so that also may change a little bit. There's some shifting going on there. All right, best thing to do is to do an example, so let's jump on an example and see how it might look like. 32 or 33? 33. So 33 says to find the area enclosed by the x-axis in the curve, x is equal to 1 plus e to the t, and y is equal to t minus t squared. Now, my first inclination in doing this is to just immediately graph it just to see how it would look like. But let's see if we could do it without graphing. I can't. You should verify that this actually is 1 to 1. a one-to-one graph, and if you know anything about e to the t just goes straight up. So 1 plus e to the t looks like it'll probably have an asymptote at 1, so it won't go below 1. So having a graph that doesn't go back down makes it a one-to-one function. So this is one-to-one, so this is okay to integrate to find the area under the curve. Now this thing is not one-to-one. It has intercepts. If you factor out a t as 0, so it's going to cross the x-axis at 0 and 1. This is a parabola pointing up or down. I think it's pointing, it's negative in the thing, in the t, so it's going down. Opening upward or downward is what I meant to say. So the graph of this would look like it goes from 0 to 1. So that's going to give a y value that's positive between 0 and 1, but exactly at 0 and 1, it'll be hitting the x-axis. So I think your graph would be very close to, not very close, it'll be kind of close to this parabola, but it'll probably tilt a little bit off to the side. Okay? Because if this is your t and your x-axis, this is your t and your y-axis, and then try to imagine when we had those 3 or 4 people up on the board that was doing this and then trying to figure out where your x and your y are, or maybe even trying to plot this, just t goes from 0 to 1, get some idea of how this might look like. It'll probably just look like this. So let's guess. Yeah, good. We did it without drawing. Let's guess that without actually drawing this, this t is equal to 0 and t is equal to 1 on your x and your y axis. Your graph would kind of look like this, and so this is the area that you're looking for. And we'll plot it to make sure that this is actually how it looks like. Yeah?
When t is 0, wouldn't it be the point 2, 0?
Oh. And then when t is equal to 1, what would it be? E to the t, e to the first power is just e, plus 1 is just 1 plus e, which is about 3.7. So yeah, good call. So what if we just move this? So this is your x-axis, and so when x is equal to 0, that's this point over here. X is equal to 2 gives you this point, and then x is equal to 1 plus e gives you that other point where it lands back on the axis. That's where the x and y bounds are, but when you're integrating this, you're going to integrate with respect to t. So we're going to focus on integrating with respect to t, which is t is equal to 0 and t is equal to 1. Did that answer your question?
Because another one, you get down to, or the other graph you made, and like the 3 things.
Yeah.
You're only looking at a section.
Yeah, I'm only looking at the section that can be integrated with respect to t.
The whole thing could be.
Well, no, because it has that, it doesn't pass that vertical. Are you talking about this example over here?
No, the one we're doing.
Oh, the one we're doing right now?
It says enclosed, the area enclosed by the x-axis.
Oh, we want to enclose the x-axis. So this probably goes down here. Yeah, it'll probably go down, and it'll probably go down this way also. When you let t go to negative or t be bigger than 1, but we just want that top part. All right. So according to our formula, our area is equal to, now I want to put the integral here from a to b of f of x dx, but I'm not going to do anything with that. I'm just saying this is f of x over here. If we were into writing this in terms of x, or y is a function of x, then that's what we would integrate. But instead of doing that, we're going to integrate this from t is equal to 1 to 2. Those are your alpha and beta limits. I'm sorry, 0 to 1. And then in here we want y of t, and then here we want x prime of t, and then we have a dt. Right? So that formula is calling for us to find y of t and x prime of t. So y of t is just this, and x prime of t is just the integral of e to the t, or the derivative e to the t. Okay. Oh boy, this looks like integration by parts. All right, while you guys integrate this by parts, I'm going to so we're going to integrate t, was it a minus? T squared times e to the t. And we want to integrate this with respect to t, going from 0, let's do it like this, t equals 0 dot dot 1. So it looks like the answer is 3 minus e. And look, that's the curve. Well, that one went from 0 to 1, huh? That's not the real curve. So this is our integral, or this is our answer. This would be easy enough to do integration by parts, right? Just it'll take like 3 steps, integration by parts. And you put 0 and 1 in. All right, let's actually graph this now in our graphing calculator program to see if what we have kind of made sense. And our function was 1 plus e to the t and t minus t squared. So if we graph this from 0 to 1, here we are. Started with 2. It ends about 2.3 or 3.7128. So that's 1 plus e, right? That we kind of guessed. And then if we were to extend this, back to Asusa's question, we went from -5 to 5 or something like that. So the graph actually extends this way. Kind of drew my graph wrong. But we're only concerned about just the top part, right? The one that's bounding the graph and the x-axis. So I think that's good. Any questions? So if you're exploring with a graphing program like this, it'll allow you to jump around and take a look at these pictures and see how those numbers relate, see how the t and the x's relate and the t's and the y's relate, and then be able to graph it. So it's a very nice advantage when you're studying these things. Okay, any questions? Done. Move on. All right, the next one is arc length, and this one is not such a nice formula. I don't know if you guys were paying attention to the video that was on before class, but she was doing some arc length of some function, and she was doing some trig substitution in terms of computing these integrals. And if you just look at the formula for arc length, already you can tell that this is going to be some problems. Not problems, but problems integrating. So this is when you start doing a problem, you run into a problem, and you give it to your 2T from Math252 and say, hey, you figure this out. Wait till they get the answer. Or you can punch it into Wolfram Alpha. So I think I just took a snapshot of what was in the book. And this is an easy enough formula to try to remember. But when we start learning more about vectors, we're going to look at this formula in a slightly different light. And when we're talking about vectors and vector-valued functions, you'll see that this idea of an arc length is going to come up again. For now, what's important for me is for you to be able to set these things up in the integral form, and then calculating an integral is not so important, because I'll assume that you've done some integral calculations in your last class, and that if you ever have this in a real life situation, you wouldn't try to do the integral by hand. Although it's good practice that you figure it out. So I guess let's just do a problem and see how it goes. Or should we try to let me give some justification without really proving it in great detail. I think this is something that's kind of easy enough to try to justify a little bit with some pictures. And it looks like they're using alpha and beta for your t. So let's say you had a curve from alpha to beta, and this is how the curve looks like. That curve could be a circle, a piece of an asteroid, or any of those parabolas that we've been talking about. The idea behind integration is to look at your problem and cut it up into little bits of pieces, and then do the linear portion of it. Not just a linear portion. I guess I'm thinking about this as a linear portion, but cut it up into little bits of pieces, and then find approximations using the little bits and pieces, and then add them all up. So that whole idea about adding up all these things and then making them smaller and adding up smaller things, and then eventually going off to an infinite number of these little things, that's what the integral is about. So if you imagine cutting this in half, and although we're not very good at finding the lengths of curves, we are very good at finding the lengths of lines, right? You can find, if I give you 2 points, you can find the distance between 2 points, right? Okay, so if I cut this into 2 pieces, or label some points and draw some lines connecting those points, we should be able to find those lines, the lengths of those lines. And the length of these 2 lines added together, although it's not exactly the same as the length of that curve, it's close enough. Not close enough, but it's fairly close. How do you make it closer? Well, cut it to more pieces. right? So that looks a lot closer than the first approximation. And then you keep doing that until you get a fine enough approximation. Or in terms of making an integral out of it, you do that an infinite number of times, and then the summation becomes an integral. That's the Riemann sum business. So it's good enough to talk about one of these pieces and try to figure out how that's going to, how we're going to be able to capture that. Well, if we label this as some change in x and we label this as some change in y, we have our right triangle business, right? And then we have Pythagorean theorem that says that the hypotenuse over here is going to be what is it?
Change y.
So that's one of the pieces that we have as a representative of what we're adding up. All right? Does that make sense? And these are all with respect to t's and stuff, and so you can imagine changing these things with a dt's and do some fancy manipulation that just looks fancy but really isn't that big of a deal. So if you think about multiplying this thing by delta t over delta t, and the delta t on the numerator can stay out here, the delta t in the denominator can go as delta t squared and then distribute to those other two things. And here's your formula that essentially becomes that when you take the Riemann sum. So that's kind of like a loose interpretation of what's happening and how that formula is derived. And again, this formula will come up again in a different context when we're studying vectors. All right, let's do an example. And unless you really have nice functions, especially the trig that simplifies to nice trig functions, unless you have one of those things, then the chances are you're going to get an integral that's going to be kind of difficult to integrate. That's just the nature of how it goes. So let's take a look at this set of possible questions and pick one. 37? 37 came up first. Oh, it's an e to the t. You know what? Doesn't matter. So once you know the formula, it just becomes really easy, right? You just need x prime and y prime, put it in. So that's exactly what we're going to do. So we need x prime of t, which is 1 plus e to the negative t times negative 1. Y prime of t is the same thing almost. It's 1 plus or minus e to the negative t times negative 1. So that becomes a plus. And then it just goes into, and they even give us our limits from 0 to 2. So our arc length, they usually call it S. I don't know why they call it S. Is that what they called it? L. They call it L. Let's call it L. So in this case, it's going to be the integral from 0 to 2 square root of 1 minus e to the negative t quantity squared plus 1 plus e to the negative t quantity squared dt. Now you can multiply this out and work it out by hand. I'm sure there's going to be a lot of fun things to do there. But they want these things usually, and in your homework also, they want things, you know, to some decimal place. So just punch it in your calculator as is and then get your result. I need to do that? You guys are all good, right? Yeah.
So on test imposes showing that and then punching it into the calculator is acceptable?
Yes.
Unless otherwise stated?
Unless otherwise stated.
Okay.
Usually for exam situations, I don't even want the answer. I just say, just what's the integral look like? And to me, that's more important because that's the concepts that's being taught in this class. Integrating is stuff that you should have learned last semester. So whether you learned it or not, I don't care. It's just I want you to learn the stuff in here.
Okay.
I mean, whether you learned it or not, I didn't mean to say I don't care. Especially when it's being recorded. Okay. Any questions? Should we take a look at a homework problem or something? Are you guys doing okay with the homework? Are you guys doing the homework?
I think it's number 6.
No, it was like the cosine of t plus t cosine t. We did that already.
Number 6, 10.2.
What? How do you guess pi over 6?
I'll show you
Yeah, but I don't like guessing. I don't like guessing your check.
What are we doing?
Number 6, 10.2.
Okay, use parametric equation of ellipse to find the area that it encloses. So that was one of the questions in our thing that you guys didn't select. So this one might be a little bit more difficult to punch in your calculator to get an answer because it's they use parameters. Well, they use parameters theta for t, but they use a and b as unknown constants. So let's work with that. So we have to agree that this particular ellipse is being drawn in a particular way so that we know how to set up our limits. So this is finding an area under the curve. It looks like just by drawing a couple or testing out a couple of points like 0, when theta is equal to 0, I have a comma 0, so cosine of 0 is 1, that gives you a, and sine of 0 is 0. So I don't know where a is exactly, but it's going to be the intercept in the x-axis. Maybe I'll try another one like pi over 2, and I know that cosine pi over 2 is 0, and sine pi over 2 is 1. So wherever b is in the y-axis, that's how my ellipse is going to be drawn. It's going to be drawn in a counterclockwise direction like this. Now, the formula that we have allows us to find the area under the curve between the curve and the x-axis. And so if I'm looking for the whole ellipse, maybe I don't care about the bottom part since this is supposed to be symmetric. I'll just find the top part and then double it, and then I'll have my area. So let's find this area over here using parametric equations. Yeah?
Can you just find the a, like you just find from the t from when t equals 0 to when t equals whatever b, and then just times it by 4?
Oh yeah, you could do that too. Yeah, that might even be easier. Should we do that? So let me change the picture and the shading a little bit. Yeah, if we're centered at the origin, this is all going to work fine. If it's centered somewhere else, then we have to do some other different things. So let's take this, let's find this A, and then we're going to multiply it by 4 to get our final answer. So we know that t is equal to 0. I didn't label it like I used to. T is equal to 0 and t is equal to pi over 2 gives me my, my limits of integration. And then I need a couple of things before I get my dt in there, and I need my y and my x prime, right? So my y is just b sine theta, and my x prime is going to be a sine theta with a negative. Derivative of cosine is negative sine, or derivative of cosine is negative sine, right? All right. So I have a sine squared. Oops, I'm using theta, so let's be consistent. Sine squared theta d theta. And I think there's a formula for this in your table of integrals, or you can remember that the sine squared splits up into the half angle formula. What is it? 1/2, 1 minus sine 2 theta, something like that. Again, you can figure that out yourselves. I will put it in Wolfram. Oops. So I'm integrating sine. I'll just integrate the whatever's inside of the integral. And then multiply it by a negative whatever. I was hoping it'd be negative, but it's not. Wonder if you need to compensate for a negative if it's going backwards. Lisa?
Was that your
Yeah.
Yeah, but you still have a negative side.
Yeah, so negative AB times this whole thing turns out to be pi over 4. And then multiply things by 4, so it looks like it's going to be AB pi. Why is it negative? Because we're drawing this counterclockwise. I don't know.
Oh, from A to B, if you have one that's bigger than the other, then flip it?
Yeah.
Yeah.
Let's take a look at the statement of the theorem here. So they make a restriction that A has to be less than B in your x-axis. And here they say x of A or x of alpha is equal to A and x of beta is equal to B. So our graph was being drawn backwards, and so we just have to throw a negative sign in front of that, I think. Yeah?
The reason I did it for that one, in order to avoid having the negative, we put the A and B and do the negative sign in there. And once we work out that math, once you do the integral, it becomes positive. And you don't have to worry about it.
That's what I thought would happen, but it didn't happen that way.
Change sign of 2 theta to 1/2 of 1 minus cosine 2 theta. And then we're going it that way, and then when you do the integral of that, it becomes positive pi something.
I think it still would turn out with a negative. Yeah, if you did it by hand. Technically, no. Because, well, no, it makes a difference. Sometimes it'll make a difference whether your graph is, whether your result is positive or negative. In terms of areas here, we should be expecting something positive. So we should have had this to be positive. But now, here's where it kind of got jumbled up, and I wasn't being precise with my math here. This area that we were looking for, let's see if I could do this in this color. This area from 0 to A, just this part. This is equal to the integral from A, or from 0 to A of whatever function that is, f of x dx. That's how it's written. Now, what they needed to do in terms of translating this into a parametric curve is that they want this limit from 0 to A to be the limits for the t. So when t is equal to pi over 2, that's when my x value is equal to 0. So the 0 over here should get matched with pi over 2, and the a over here should get matched with t is equal to 0. So in doing that integral, when your limits are switched, you're going to generate another negative sign that will cancel out with this negative sign. So this is probably, this is what we should have done if we would have done it carefully. And we should have done this with pi over 2 to 0, and then that integral, because the lower limit is larger than the upper limit, it'll switch. Wow. Does that make sense? Yeah, your limits of integration should be based on your x values. And then the bottom line is, if it's an area, you should have a positive value. So if you got a negative number, chances are there's a small error like that that would make it positive. All right, so AB pi is what our answer is supposed to be. Yay. Okay. So that worked out. Any other questions? 10.1? Have to be more specific. All right, circles. Parametric equation, path of a particle that moves around a circle. And here they give a circle. And then enter your answer as comma separated list of equations. X is equal to something, y is equal to something. So let's see if we could jot down a few things here. If you can't already picture the circle, then have some sort of graphing device that will help you picture the circle. The circle is offset to go up along the y-axis by 3 units, and it has a radius of 4. Okay? So I see the circle kind of looking like 1, 2, 3, and it has a radius of 4. 1, 2, 3, 4. Okay, so it should look kind of like that. And the first one, once around, starting at the point 4, comma 3, which happens to be our usual starting point for the circle. If you look at our circle in standard position, we start at the point 1, comma 0, and then we rotate around counterclockwise. So we want to rotate clockwise this time. So we start at this point, and when So our standard circle is cosine t, sine t. All right. So the shifting up 3 units just means along the y, I would add 3 units to it. So I would just add 3 to the y. So the shift up, x equals cosine t, y equals sine t, and then add 3 to it. So that's a shift up. Now, let's do a few things. Let's do what they're asking us and see if we can extend our ideas and do a little bit more. By the way, this thing draws a full circle from 0 to 2 pi, right? So if we want to go, instead of the clockwise direction, go the counterclockwise. Instead of the counterclockwise direction, we want to go the clockwise direction. We're just changing the orientation of t, right? So any suggestions on how to do that? Put the what? If you switch them, you might start off at a different starting point. Change the signs. So to go clockwise, basically to go the opposite way of the direction that you originally had, all you need to do is put a negative in front of the parameter, the t. So a negative cosine of negative t, and sine of negative t. You guys know what happens to cosine of negative t? It's just cosine t. It's an even function, so that's not that big of a deal. But having a sign, having a negative sign for t here will make this negative. And so this will draw your circle backwards. Okay? So that's probably what I would put here. Now it says 4 times around, going from starting at 4, 3. Yeah.
You have to change the radius, right?
Oh,
Yeah.
sorry. Shift up. Radius 4. So just multiply the sine and cosine by 4. Sorry. That was. All right. So that's a clockwise business. So again, I'll probably put x is equal to 4 cosine t, y is equal to 4 sine negative t plus 3, or something like that. If I want 4 times around from 0 to 8 pi, I think for each 2 pi I finish one circle, and this is just going to go 4 times around. So the standard shift up I think will do. So this one is going to be x 4 cosine t, y, you want a comma in between, y is equal to 4 sine t plus 3. So the last one, they want halfway around, counterclockwise, starting at 0, 7. So 0, 7 is up there. You want to go halfway around from 0 to pi, so it'll be kind of like the standard, except you're not starting at 0 here. You're not starting in our standard position. You're starting at the higher position, and you're going counterclockwise. Yeah. You could flip the cosine and the sine then, but then you're going to be going in a clockwise direction. So you can flip the cosine and sine, add the negative, is one way to do it. But I wanted to show you another way to do it where you're shifting. So if you wanted to do a shift, we could do a shift in t where instead of, imagine that this is your t is equal to 0 and this is your t is equal to pi over 2. All right? So what you could do is you could take that same function that we had and then if you tack on a pi over 2 to it, then it would have gotten started pi over 2 ahead. And so this is going counterclockwise, so it's going in the regular direction. And the thing is, whenever you do this, you always want to check with your handheld graphing calculator or graphing calculator program like this to see if that's actually what's happening. Because sometimes it's a guess and check, and when you guess, and it's wrong, then you're going to get marked off wrong, right? Okay, so let's actually check our answers. You think we should check any? Or should you guys just trust me? What did we decide for this one? Cosine t. Can you copy and paste here? And this one we decided cosine t plus pi over 2. And I don't know if this is going to be all correct, but I wanted to see if we could change our answers too, to see if we can, you know, that idea about switching. If we switch to sine and cosine here, so if you switch it to sine and cosine, remember that this is going to go in a different direction. So if we want it to stay in the same direction, we put a negative in front of the t with a sign, and it should still work out okay. So that still worked out okay. Oh, another thing about the sine and the cosine, sine of negative t is the same as negative sine of t. So if you had put the negative outside, it should also work. So the thing is that there's a lot of different ways to express this, and here it's not. It's because of the trig identities that we have, but you're expressing the same function. But you'll see that there's a lot of ways to generate the same curve with the same set of restrictions with different types of functions. That's parametric equations. All right. Okay, I think our next topic is going to be on polar coordinates. You guys might have a quiz tomorrow, so be ready.